A wave of small earthquakes shaking Mount St. Helens in recent days, and experts say more than 100 quakes have actually occurred.
There was a cloud of ash spotted blowing at the peak of Mount St. Helens.
USGS has just issued a red alert after scientists detected what appears to be a secondary magma plume extending deep beneath Mount St. Helens. This startling revelation suggests that beneath the familiar dome and crater, a new subterranean artery of molten rock is asserting itself, threatening to rewrite what we understand about the volcano's internal plumbing. The discovery of such a plume, branching away from the main magma system, is not just an incremental uptick in hazard, it speaks to a more complex scenario, one that raises profound questions about the volcano's near-term behavior, possible eruption paths, and regional risk dynamics. Before we start, hit the like and subscribe buttons for more exclusive news. Magma systems are rarely simple. Beneath active volcanoes, molten rock may collect in chambers, flow through conduits, stall in reservoirs, or even sprout offshoots into less expected zones. The traditional view for Mount St. Helens has involved magma rising from depth, accumulating in a subsurface storage region, feeding the present dome-building activity, and occasionally driving explosive episodes. But the appearance now of a subsidiary plume implies that there is either a new source of magma input or a branching pathway that was dormant until now, and science is racing to interpret its geometry, volume, and connectivity. What led to the red alert was a convergence of geophysical signals. Ground deformation monitors, GPS stations, tilt meters, INSAR satellite radar observations began to record subtle inflation not merely adjacent to the known dome complex but offset laterally, away from the main vent area. At the same time, seismic arrays captured a pattern of tremor and low-frequency events in zones that had not shown such activity in recent years. These signals suggested magma movement into hitherto quiet sectors of the volcano's edifice. Inversions of seismic wave velocities, using tomography and seismic imaging, revealed an anomalous zone of slower material, consistent with partial melt, extending laterally from the central magma reservoir. Other instruments, such as magnetotellurics, may also show conductive anomalies in that same location, reinforcing the inference of molten or hot fluid presence. Putting those observations together, volcanologists have concluded there is enough evidence to warrant a red alert. The volcano is entering a heightened unrest phase with serious potential. Crucially, the red alert does not necessarily guarantee an imminent eruption, but it marks a shift from potential hazard to probable hazard zones. In practical terms, it means closer monitoring, widespread readiness, and reassessment of hazard zones, particularly in directions aligned with the new plume's footprint. The very existence of a secondary magma plume changes the conceptual model of Mount St. Helens. Rather than a single branch supply from depth to the dome, the volcano may now behave more like a branching tree. Multiple feeder channels may operate, compete, or interact. One branch might feed the usual dome extrusion, while another could surge toward a flank or side pathway, potentially opening a new vent away from the main crater rim. This complicates hazard mapping, because areas once considered safer, those sidelong flanks, ridges adjacent to the volcano, may now lie under threat. Such a new conduit might tap a different structural weakness in the rock, a fracture zone, fault line, or zone of hydrothermal alteration that is mechanically weaker. If magma uses that pathway, eruption could occur outside the traditional crater boundaries. Lava, pyroclastic flows, or ash-emitting explosions might originate from unexpected locations, potentially catching populations or infrastructure off guard. Risk zones might need to be recalibrated laterally, not just uphill or downstream. Another implication is the possibility of magma mixing and pressurization interactions. If a secondary plume is connected, even weakly, to the main magma chamber, pulses of magma injection into that branch could alter pressures system-wide. The branching might relieve pressure along one route, but also trigger stress changes in the adjacent rock and magma. That in turn could destabilize the primary conduit or dome, provoking explosive ruptures. Moreover, if magma in the secondary plume comes from a slightly different composition, perhaps hotter, more volatile rich, or from a deeper source, mixing with existing magma might lead to gas exsolution, fracturing, or sudden eruptions. Volatile behavior is central. As magma ascends, dissolved gases, water vapor, CO2, sulfur species, decompress and exsolve, forming bubbles and increasing the propensity for explosive activity. A secondary plume could bring a fresh batch of volatile-rich magma into the system, altering the pressure-gas equilibrium. If that magma meets more viscous, degassed magma in the main reservoir, the mixing could nucleate bubbles explosively, creating overpressure and fragmentation. That process is among the mechanisms thought to drive sudden high-energy eruptions. The spatial orientation of the plume also matters. If the branch trend is toward a flank that overlooks populated regions or critical infrastructure, roads, towns, power lines, rivers, those sectors move into higher risk categories. Emergency planners must contemplate lateral hazards, pyroclastic surges traveling across ridges, ash columns that might drift into inhabited valleys, or ballistic ejection zones beyond currently mapped areas. Because the plume is secondary, current hazard maps may not extend far enough in those new directions, so updating evacuation boundaries will be essential. From a monitoring and forecasting perspective, the discovery forces the USGS and affiliated institutions to refine their sensor network. New stations, seismometers, tilt meters, GPS receivers may need installation nearer to suspected propagation zones to resolve spatial detail. Satellite-based INSAR campaigns will increase in frequency, and airborne surveys, gravity, magnetics, gas flux, gas chemistry, will gain urgency. High-resolution imaging of ground cracks, thermally anomalous zones, or fumarole patterns may catch precursory signs of magma migration along the new plume. Numerical modeling of magma flow and stress fields must be updated. Researchers will compute how much magma is being diverted, how pressure fields evolve, and whether the branch is stable or liable to sudden jumps. Simulations of conduit failure or conduit switching will inform potential eruption scenarios. Volcanic gas transport models will project how gas emitted from the secondary path might disperse, and ash dispersal models will be adjusted to include potential eruptive vents along the new channel. One of the most ominous possibilities is that the secondary plume may accelerate destabilization of the edifice. As magma intrudes into newer zones, fracturing and rock weakening could occur. Crustal stresses might shift, possibly triggering landslides or sector collapse, especially in thermally altered rock. Hydrothermal systems, groundwater heated by magma, could play a dangerous role. Pressurization of steam, heating, water-rock reactions could trigger phreatic blasts or sudden vaporization. If the branching magma interacts with saturated zones, steam explosions are a risk, even before full magma eruptive behavior occurs. Moreover, fluids, hydrothermal or meteoric water, could infiltrate incipient cracks opened by magma intrusion. That water might carry heat, weaken walls, or provide a reactive medium. In worst cases, melt zones could partially collapse, forming cavities and instabilities. The secondary plume geometry might evolve over time. It could grow in volume, migrate laterally or upward, or stall and then reactivate. Continuous mapping of the plume's evolution is critical to assess whether it is transient or persistent. Communication with stakeholders becomes more critical. The red alert must be accompanied by clear messaging to nearby communities, public safety agencies, aviation authorities, and federal agencies. The possibility of eruptions from new vents must be explained, although certainty is impossible, and response plans adjusted. Airspace in the region will need review because ash or steam plumes from new angles might intersect flight corridors. Emergency plans should consider alternative evacuation routes that avoid possible flow paths from newly threatened sectors. Scientific curiosity and urgency must balance caution. It may turn out that the secondary plume is incipient, small, or even ephemeral. Magma may intrude and then stall without reaching the surface, but even such aborted intrusions can do damage, fracturing rock, generating seismic swarms, raising gas release, and destabilizing hydrothermal systems. The red alert status ensures that scientists will scrutinize even minor anomalies with urgency. In terms of volcanic hazard assessment, this event forces us to rethink risk levels. Before, hazards might have been concentrated in the crater and valley directions. Now, flank hazards gain prominence. Some areas previously deemed safe might now lie within reach of lateral eruptive phenomena. The risk matrix for lava flows, pyroclastic density currents, ashfall, lahars, ballistic ejecta, all must be recalculated considering multiple possible vent sites. International comparison is instructive. Other volcanoes that have had branching magma systems, such as Mount Etna, Kilauea, or volcanoes in the Andes, have sometimes launched new fissures, flank vents, or satellite cones. Those systems taught that feeder plumbing can be dynamic, reconfiguring over time in response to pressure changes, magma supply, and structural stresses. If Mount St. Helens is now displaying that behavior, it is entering a more polymorphic, less predictable state. Scientists will also want to probe the source of the secondary plume. Is it fed from the same deep reservoir as the main conduit? Or does it tap a deeper, more primitive magma body? Geochemical sampling, gas ratios, isotopes, trace elements, could, if eruptive materials emerge, help distinguish magma sources. Temperature estimates from melt inclusions or thermal remote sensing may show hotter magma in the branch. That, in turn, might inform how forceful future eruptions could be. Timescales are another critical factor. How fast is magma migrating in the secondary plume? Hours? Days? Weeks? If signals indicate acceleration, that would suggest motion is imminent and surface activity might follow. If the intrusion is slow, scientists may have more lead time. But slow intrusions sustained over months also impose long-term pressure. Public memory of Mount St. Helens is haunted by its 1980 eruption, a catastrophic explosive collapse of the north flank and a colossal lateral blast. That history reminds us that volcanoes can surprise us with lateral eruptions, sector collapse, and unexpected vent location. A branching magma plume evokes the specter of lateral blasts or flank eruptions, raising specters of sudden hazard shifts. One must not overstate certainty. Uncertainty is large, and volcano systems often tease before erupting. But issuing a red alert is a serious step. It signals that monitoring agencies regard the volcano as being in a state of likely escalation. It is a call to higher vigilance, stronger readiness, and more robust modeling. Emergency agencies must assume the possibility of eruptions somewhere along that new pathway. A secondary magma plume might not erupt immediately. It may stall, clog, dega without breakout, or feed sills. However, the pressure changes it induces could still destabilize adjacent magma or rock. So scientists must watch for correlated signs, spikes in seismicity, changes in gas emissions, new thermal anomalies, fresh cracks or deformation, or shifts in hydrothermal fumaroles. For the public, the implications are unsettling. People living downwind of the volcano may need to consider alternate ashfall scenarios. Residents near flanks formerly deemed low risk may face new exposure. Tourism, forestry, park operations, and transportation corridors might need to be rerouted or suspended depending on evolving forecasts. The USGS and state agencies must update hazard maps, issue advisories, and possibly prepare for evacuation protocols in sectors not traditionally considered. For aviation, the possibility of ash plumes from new vent angles demands vigilant airspace monitoring. Ash is a known hazard to aircraft engines, and an unanticipated plume emerging from a flank vent could catch planners unprepared. Early integration with the NOAA, FAA, and aviation warning systems is essential to ensure planes avoid newly threatened corridors. One technical challenge will be discriminating magma signals from non-magmatic ones. The inflation or seismic signals might, in principle, reflect hydrothermal fluid migration, tectonic stress shifts, or other processes unrelated to magma. But the tomography and velocity anomaly data gave scientists confidence in interpreting a melt-rich intrusion. Still, continued multi-parameter correlation is essential to avoid false alarms. In coming days, weeks, and months, the new focus will be on tracking the plume's evolution. Will it propagate upward, intersecting shallow crustal layers and potentially extending toward the surface? Or will it branch further, fan out, or stall? Will magma accumulate and pressurize, or slowly leak gas and dwindle? Each path carries different probabilities for eruption style: effusive dome growth, explosive blasts, flank venting, or phreatic explosions. The red alert also marks a shift in how scientists publicly frame Mount St. Helens' hazard narrative. For decades, much attention has focused on the crater dome itself, on rockfalls, gas emissions, and occasional dome growth. Now the narrative must incorporate a potentially complex network of magma pathways. That complicates communication. Scientists must convey uncertainty while ensuring public preparedness and trust. One particularly vivid scenario science must prepare for is the possibility of dual venting. Magma might erupt simultaneously from both the original crater and a flank vent, That would stretch resources, complicate hazard zones, dual plume dispersal, and multi-directional hazards. Resource allocation, evacuation, monitoring, response units would have to adapt rapidly. Another scenario involves stress transfer. As magma intrudes into one branch, it could relieve pressure in one direction but increase stress in adjacent rock volumes, triggering rupture or opening new fractures. In effect, the volcano could reconfigure itself mid-shock, opening vents in places not anticipated. That metamorphic and mechanical flexibility is part of what makes volcano forecasting so difficult. Thermal considerations also demand attention. The new plume will carry heat into surrounding rock, expanding thermal halos, altering local rock strength, and possibly triggering creep or crack propagation. Those thermal effects might precondition walls or conduits to fail. Subsurface rock melting, alteration, or weakening zones might expand outward, destabilizing the edifice gradually. Hydrothermal systems are a double-edged sword. On one hand, they offer a pathway for fluid communication. On the other, they inject pressure and corrosion, further weakening rock around the plume zone. Steam, gases, and latent heat can erode weak zones, widen fractures, and lubricate potential collapse surfaces. Monitoring of gas chemistry, fumarole flux, temperature, and pressure in hydrothermal wells will inform whether the plume is interacting with water. In the geological record, multiple eruption events often involve complex plumbing enhancements, new feeders, composite plumbing architectures, tapering dikes, sills, and branching networks. That the plume appears now could represent initiation of a new evolutionary stage of the volcano's plumbing system. It might herald a period of more frequent reconfiguration, more complex eruption behavior, or greater volatility. One should also consider magma supply rates. If the deeper source is injecting magma faster, the secondary plume may act as a pressure relief valve, drawing off magma. But if the supply is limited, that new branch might starve the main channel or cause competition. Competition in magma flow is a known phenomenon. Branching systems may alternate dominance, leading to pulsing eruptions, stepped vent switching, or lava lobe migration. In time, if eruption begins in the secondary pathway, scientists would closely examine the morphology of emerging vents, fissure versus point vent, alignment with structural fractures, relation to pre-existing faults, that would then feed back into structural models of the volcano's crust. The orientation and strike of the plume may reveal hidden faults, stress axes, or rift zones previously unrecognized. The recognition of a secondary magma plume beneath Mount St. Helens also reignites interest in the broader tectonic and magmatic architecture of the Cascade Range. This chain of volcanoes owes its existence to the subduction of the Juan de Fuca plate beneath the North American plate, a process that continuously melts portions of the subducting slab and overlying mantle. Mount St. Helens, being the most active volcano in the continental United States, sits near the forefront of this immense tectonic collision zone. The discovery of another magma conduit could hint that subduction processes are evolving locally. Perhaps the angle of the descending slab or the thermal flux at depth has shifted, feeding magma in new directions. The plume could therefore represent the first visible symptom of a deeper geodynamic rearrangement under the Southern Cascades. That possibility intrigues geophysicists because it may mean magma is beginning to exploit new fractures in the crust, reshaping the plumbing not only of Mount St. Helens, but possibly influencing neighboring volcanic centers. There is some evidence, gathered over decades, that the magmatic systems beneath the Cascades can interact laterally through deep crustal melts. If the secondary plume connects to such a network, it might signify a regional migration of magma, or even a shared reservoir boundary. This connection would complicate eruption forecasting because pressure changes in one volcano could trigger subtle responses in others along the chain. The heat flux measured at the surface will become an invaluable diagnostic tool. Even minor temperature increases in soils, fumaroles, or crater lakes could point to the upward creep of magma. Spectrometers mounted on drones or satellites can capture infrared signatures invisible to the human eye, mapping the faint glow of warming rock. These thermal gradients can help delineate the evolving shape of the magma body, revealing whether it is spreading horizontally, feeding vertically, or beginning to decompress gases into overlying strata. Combining these readings with seismic velocity data provides a dynamic picture of the molten core in motion, alive beneath a seemingly calm mountain. Another profound implication of this development lies in our understanding of volcanic life cycles. Many volcanoes experience alternating periods of dormancy and reawakening as new magma intrudes into old conduits. The secondary plume may represent not just a short-term episode of intrusion, but the early construction of a new volcanic edifice within the mountain itself. Over geologic time, repeated injections could build a fresh magma storage complex, eventually birthing a new vent system and transforming the silhouette of Mount St. Helens altogether. This is how composite volcanoes evolve, layer by layer, intrusion by intrusion, their structures reflecting a long memory of shifting pathways and magma supply lines. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on Mount St. Helens' new magma plume? We want to hear from you. Thank you for watching, and see you next time.